So you all know Ben. Ben is professor of environmental management at Hopkins University. He's one of the organizers of this workshop, so we're all grateful to you for the work you've done. And Chris is going to be the
Thank you, Natalia. Voila. Okay. So I think Ramteen's talk does raise the issue of who is the leader in this market and why is there's a lot of storage papers where the storage is the leader, and Natalia's question raises a very good point of why are we assuming one structure versus another. In cases like the Pacific Northwest or in Brazil, where you have huge storage facilities, I can see storage being the leader, but I think this is a rich area for people in industrial organization to study and actually inform us, the modelers, as to what sort of structures are we seeing that could lead to the emergence of market power. And it might not be storage as a leader. So this talk is one of several, this meeting that's addressing capacity markets. We heard Par and Bert talk yesterday. Jacob Mays, there he is. It's going to take later this week. I'm glad Jacob's going later because he's going to show why all of our conclusions are wrong because we ignore risk aversion in financial markets, which, Bert, you've reminded us repeatedly in the past that ignoring financial markets is a big mistake, but I guess you have to walk before you run with that market. But anyway, I imagine you folks have a lot to talk about. I'm going to be looking at a pretty practical question, which is in U.S. capacity markets, we give capacity credit to renewables, but what are the efficiency implications of giving the wrong credit? And there are all sorts of reasons why the wrong credit does emerge. So first I'll show, and this just confirms results that you've seen earlier, that capacity markets in a world of risk neutrality can in theory provide supporting prices. You don't need a ramp product and other things. But you have to count the credits right. Is it 14% or 12% or 23%? If you have an error in capacity counting, then you get inefficiencies. And I'll talk about a little bit about the sources of those errors and then the implications for the primal solution. What does the market give you in terms of endogenous investment? And then losses of economic efficiency. We've had a bunch of great motivation slides, so I don't need to show you too much in that way. But of course, the contribution of renewables to meeting peak demands is varies from year to year, and also there's also long-run uncertainty. David and I hosted Peter Meyer at EPRG 10 years ago, and he showed how average wind speeds in Southeast Asia and Vietnam have plummeted over the last 20 years. So as a result, there are a lot of wind turbines that are sitting there and essentially not spinning. So there's long-term uncertainty too, which we haven't talked about. And that's of course true with thermal outages as well. Talk to me about nuclear plants in California, for example. Nevertheless, there is a real contribution. We just don't know what it is. So I'm going to ask the first basic question: is there a way to count capacity credits that would incent the economically efficient welfare maximizing portfolio of resources in this imaginary static world of no risk averse players? And then, okay, now let's give them the wrong credits and see what happens. What sort of distortions do we get? So as motivation, this shows wind patterns in Texas at a particular location over 10 years, and of course there's a lot of variability. What you don't quite see is there's a lot of year-to-year variability in the averages as well. Unfortunately, at least in Texas, you can see the demand peaks don't quite coincide with the wind peaks. Sometimes they do, but often they don't. And this is what a planner has to deal with. What sort of capacity credit should we give this wind? So if you build wind, you don't have to build some combustion turbine or something else. This is the case that if we, at least in theory, if we make mistakes in market design, The results can be catastrophic. California 2001, 2002, of course, was an example of that. I don't know whether he remains smiling for long. Okay, that's a typical March day in Cambridge, right? Usually it's warm enough to go swimming. Okay, so here are some hypotheses of giving the wrong credits, too much or too little. What happens if we give too little credit? There are some markets where wind gets no credit. What if we give too much credit in we want to feel generous and encourage these resources, so we'll give you some more capacity money. And what if, as is the case in many markets, we don't differentiate capacity credits by location? The resources are of different quality, there are transmission constraints. So, of course, if we undercredit capacity, we might wind up then building too much stuff to meet a reserve margin constraint. For that particular capacity type in question, though, maybe that you'll build too much, it may be that you'll build too little. In a sense, the elasticity of the equilibrium capacity with respect to the credit might be positive or negative, and we see instances of both in our simulations. And for other types, if you undercredit some capacity, other types, you're going to build stuff that doesn't get used. If you give too much credit, you've got an under-reliable system in equilibrium, and once again, the sign of the effect for the particular capacity type is ambiguous. And finally, this turns out to be important in our case study. If you don't differentiate, you get an insufficiently diverse renewable mix and higher costs. And at least in Texas, we wind up biasing the renewable portfolio towards resources that have a higher capacity factor. It turns out that sometimes resources with low capacity factor contribute more capacity because they're simply adding diversity, or maybe the profile coincides with loads. Okay, so here's the upshot. This is where I'll wind up in terms of guidance on credits. If you're trying to minimize the expected cost of investment and operation, okay, I'm going to be in this imaginary inelastic demand world, where you've set a reliability standard and you're trying to hit that, the first thing you need to do is set the credit per megawatt hour such that you equalize the reliability value of one equivalent credit of wind with one equivalent credit of demand response or batteries or whatever else. So this has been something articulated by system operators. Actually implementing it numerically is not an easy thing to do. You have to recognize several things. First of all, the marginal contribution of wind resource, is generally less than the average contribution. But in most markets, they look at the average contribution over the entire portfolio of wind rather than what one incremental megawatt gives you. So if you ignore the marginal contributions, you'll be off. If you ignore the effective location, you'll be off. And then finally, this is a point that Dick made. When does the peak occur? Well, with more and more renewables, the peak is not that August day in Texas. It might be some other day, a calm day in the spring or somewhere else. And when this occurs, of course, will be a function of penetration. That should be recognized, but in many systems it is not. The second thing, the second principle that you have to do is that you have to set the sum of capacity credits that need to be provided by the market has to be set at a level such that you meet whatever the reliability standard is, the 1 day in 10 year or whatever else. And that will be a function of the credit. It turns out the credit values. You have to determine both of these simultaneously. So what's going on is there's an energy price cap, which causes this missing, in theory, this missing money thing, and you get underinvestment. And once you have the energy price cap, then there's going to be an optimal set of credits to award, and then a reserve margin, and then the market will provide payments according to your credits. Okay, so capacity markets can, in theory, work, and I'll be looking at markets where folks are making choices among generation types, perhaps including demand response and storage. the simplest case will be where if you have a price cap market, you're selling both energy and what's called resource adequacy in California, or capacity. There could be other stuff that's sold too, and actually our market model includes renewable credits, but those could also be in the mix. I'll be focusing on the impacts of certain inefficiencies, in particular having a price cap on energy interacting with inaccurate capacity credits and thus inaccurate capacity payments. There are all sorts of other market failures that one could look at, but I hope this framework of Cindy's is flexible enough to accommodate those. So first of all, the theoretical result. So let's start out with an equilibrium problem in an energy-only market where consumers will have an inelastic demand except if the price exceeded the value of lost load. And so here are the players in the markets. Consumers maximize their net value. Generators are maximizing their profits subject to their production function or capacity constraints. And then you have market clearing for energy. And then if you have a capacity market, you then have a reserve margin multiplied by some peak, and your capacity credit per type of generator times the capacity provided has to exceed that. So they're acting independently. So they're maximizing consumer surplus, they're maximizing profit, and the markets have to clear. So in the energy market model, where the price can go up, the value of lost load, the brave world of Texas and Australia, there's no market failure. You get an optimal amount of reliability. In the second market, I then put a price cap on this. So essentially, the market treats consumers as valuing power a lot less, $1,000 rather than $10,000, and you get a different equilibrium. But nevertheless, even though you have that distortion, if you set Rm correctly and beta correctly, you can show that you get the solution to Model 1. You get the welfare maximizing solution. You have the wrong values, you get a loss of efficiency. But in theory, with perfect information, we set these things right, we get the same solution. And I think Parr showed something similar to that yesterday. Okay, so that's an equilibrium problem. I need to calculate the equilibria, and Cindy does that using linear programs. So the top one is a linear program that chooses capacity levels, generation from each of these. We could throw in storage and demand response if you'd like. In fact, we're doing that. It is maximizing the value of demand minus the cost. Classic Samuelson maximize welfare to simulate a competitive market. And then in the capacity market, we replace VOLL with the price cap to simulate that, and we throw in the capacity market. So that's the interpretation of each of these. What we've done with simulating the capacity market with the price cap is that we've got a pseudo welfare that has a lower value for consumers, but we have this capacity market. And so the task is to show the solutions of these two can be precisely the same with a careful choice of beta and reserve margin. So the propositions, first of all, are that that linear program gives us, this linear program here gives us the market equilibrium I showed before between consumers and producers and market clearing, and that the LP for the capacity market also gives you the market equilibrium between independent generators, storage, and consumers, and so forth. So we have to prove this equivalence, and then finally have to show that there exists a set of beta and a reserve margin such that you get exactly the same solutions. The solution one is a solution to the other, and so a capacity market can be efficient. And so this is just the classic approach to this sort of thing, where you showed that basically the Kuhn-Tucker conditions of the linear program are the same as the equilibrium conditions of the market where everybody behaves independently. And so this shows that this is the market equilibrium problem. There's the linear program, and take each of their Kuhn-Tucker conditions, pile them up in one big pile together with market clearing, and you'll have the same conditions as for this optimization. Ditto with Model 2. Okay, so the first two propositions can be proven that way. That's pretty routine. The third proposition is the equivalence of the two models if you're clever. And so we demonstrate this, and I have an appendix of 8 slides if you want to see it. I'll spare you, though, especially before lunch. What we do is we have possible realizations of capacity availability: wind, sun, hydro, and these are discrete states. And then we have a smooth load duration curve. And I have a smooth load duration curve rather than discrete loads because we want to avoid degeneracy in prices in the spot market, which is really annoying. And then finally assume that generators are ordered by merit order. So if the merit order was endogenous because we had a carbon limit or something, this would get a little more complicated, but I don't think it destroys the result. But this makes the proof easier. So all the generators, gas, coal, nuke, or whatever, are ordered by merit order. And you have these discrete capacity states and continuous low duration state. And then basically it's what Steve Stoff did in his book, a bit more elaborate. We develop versions of this model that correspond to models 1 and 2, and we show that the solution of 2 is the same as 1. The first order equilibrium conditions are the same if the capacity credit equals the expected output during hours of unserved demand, or more generally hours of shortage of operating reserves. So you have to identify those hours and then calculate that. That's essentially what you do in effective load carrying capability type analysis. And then you choose a reserve margin, choose this thing in the constraint. You make it high enough such that the weighted capacity from model 1 just equals that reserve margin. So if you've chosen RM and beta that way, then model 1 and model 2 give the same solution, and we've got the result that we want. So in theory, it's possible to do. You don't need to pay separately for flexible capacity, for example. There's no, you've taken care of the market failure of the price cap. All right, so those betas, where do they come from and why can they be mistaken? Well, politics, we want to make things simple and transparent. That is a noble ideal for market design. And perhaps we want to give the benefit of the doubt. If we don't know the capacity credit of renewables, we haven't done the studies, we'll assume some relatively high value. And then maybe in a misplaced desire to be fair, we'll say, well, all solar will get the same credit, no matter whether you're in East Anglia, which is sunny. Have any of you noticed that there's prickly pear cactus along one of the bike trails here? It's sunny here. Or up in Manchester, where it's very cloudy and rainy. But to be fair, maybe we'd give the same credit to both. So an example, the cappuccino, CPUC, we call it fondly the cappuccino, rules where they assign the average effective load carrying capability to all resources. Look at all wind, the capacity that adds is so much, and then we just give that average, rather than recognizing that there's diminishing returns. It's bad to be called cappuccino. It could be worse. There's the Ohio Public Utility Commission of Ohio, which is fondly known as PUCO. So, okay, so take that. If we don't know what, if we haven't studied for a new site, we simply give it the system-wide average value for the first 3 years, which may be generous or maybe not. At any rate, 3 years is a long time in this business, so that could distort things. Okay, another source is that we confuse average and marginal contribution. So you know from economics, of course, that marginal revenue lies below the price curve. So here are some examples for Texas. Cindy simulated this. The average capacity contribution as a function of wind penetration is strongly decreasing, and if you take, and then if you look at the marginal contribution, it's even less, on the order of 5%. And here's some well-known stuff from the literature. ILEX is I believe that's now called Pyomo. What's the name of the consulting firm? Anyway, they did a study of the UK system, and these are some other studies. They showed that the average capacity contribution of wind to the UK system is decreasing from 35% to 20% if you get up to 40% wind penetration. But of course, the marginal contribution is double the slope. And so the marginal contribution is below 10% at these sorts of penetrations. And this is what beta should be, not this. So you may be getting more than twice as much credit as you should if you base it on average. Dick's point about not knowing where the peak is, system peak in Texas is July 13th, 2009, but if you add a lot of wind, the new system peak is instead June 24th. And the contribution of wind to reducing that peak is very small here, is something on the order of 10%. So if you insist on calculating renewable capacity credits based on the peak demand day, you're going to miss the fact that if there's diminishing returns, this peak will shift to times when the renewables are less effective, and you'll be overestimating beta. And a lot of ISOs do this. Another problem, and so there was a poster outside that I haven't gotten to meet the authors yet, that show huge year-to-year variations in wind production. And so this is in Texas, and so this is about 25% higher than this. And many capacity credits calculations are based on a single year or 3 years. So sample error is a real problem. This is even ignoring Peter Meyer's issue of climate change drastically decreasing wind speeds in Vietnam. At any rate, that can result in wrong capacity credits. So what I will now show, after talking about what the ISOs do, I'll show the practical implications of this. Okay, so this is what ISOs with capacity markets do, and then in Texas, they do calculate capacity credits, but they don't actually pay. And so this is a table that Cindy has prepared of all the different rules, and they vary all over the place in terms of how much data you consider, from the last year to the last 3 years to the 10 years, to which hours you consider. Most consider the peak, the system peak. They don't consider the shifting peak. None of them consider the marginal value. They all are considering some sort of average for the class of resources. There's no industry standard. FERC, where are you? Well, I guess it's not, maybe you don't think it's your job to, to impose a particular way of doing this. But what you see as a result of applying these different methods to the same data is hugely different capacity credits for wind, from over 30% to something more like 10%. Okay, so let's look at the implications for generation mix and economic efficiency of these eras. So this is a Texas system where we assume 2013 load and certain capacity factors for 3 different wind sites and solar sites. The wind sites, there's some diversity, and we have EIA, Department of Energy type costs for different capacities, except for coal. This is going forward costs for existing facilities. Anyway, so a bunch of stuff, and we throw this into a large linear program for 10 years, 87,000 hours. We solve Model 1, where we assume VOLL is $10,000, and then we solve Model 2 with a price cap of about 1/8 of that. and we then throw in the capacity mechanism to make up for that price cap. And the credits are added up, and they must meet the demand for that. And the distortions, you get distortions because the investments are biased by the price cap, suppressing revenues, missing money, but the inefficient capacity mechanism doesn't make up for it quite correctly. All right, so we could compare them in all sorts of objectives: carbon, loss of load, mix, and costs, and this would be an 8-dimensional diagram. I'm going to simplify things. I'm going to assume that every market design has the same level of adequacy. We're hitting the same LOLP target. I basically adjust the reserve margin to hit that. And so then the only differences, if we ignore emissions, the only differences are the generation mix and the cost. That will simplify the comparison. So let me show that. Model 1, the optimal reliability is this. This is the loss of load, expected unserved energy in megawatt hours per year, about 13,000. That's if there's no price cap. If there's a price cap, you're going to build a lot less unless you have a capacity market. So what Cindy does is just numerically adjust the reserve margin until the outage level hits the reliability standard. Then you compare the cost of Model 2 with that capacity market, with this reserve margin, with Model 1. And in this case, if we give no credit to wind and none to solar, we're increasing annual costs by 26 million. Now, on the other hand, if we give solar a huge credit, 75 or 100%, and give wind more credit, we get even more distortion. We search for the level of the reserve margin that hits this reliability standard, and then look at the cost. So it's 80 or 87 million. This is a measure of the efficiency loss. And we can look at the capacity mixes, and we see with the wrong credits, we get different mixes of wind and solar. We get more solar with the high credit, more wind with the low, even zero credit, and you get some adjustment in coal and CT. And so the cost losses we're talking about are about 0.5%. The optimal betas are surprisingly small. If you have no RPS, the optimal beta is 7% for one of the wind sites. The others aren't developed. If you have a 40% RPS, the optimal betas differ among sites. Interestingly, the site with the lowest capacity factor has the highest optimal capacity credit because there's less penetration there, and its pattern coincides more with load. Hardly uniform. And then for solar, it's 28%. This also shows diminishing returns. As you add more wind site 3, its capacity credit should go down, and we have locational variations. By the way, you might have noticed there were some negative reserve margins. That's because of diminishing returns. Thank you. The marginal credit is less than the average credit, and so the optimal RM turns out to be negative, which sounds kind of funny to a power engineer. But in fact, that is the case. These credits plus this reserve margin give you the social welfare maximizing solution. We talked about how we might actually do this in California, and the discussions didn't get very far because of the political optics of paying for seemingly less capacity than the peak load. And then some other things blew up politically in terms of merging the capacity markets of the West. Okay, one last slide of results. This is looking at the impacts of sample error. So I'm assuming the process is stationary, but we have random variations year to year, unlike in Vietnam where there seems to be some trend. So if we take all 10 years of data and treat that as the true value, we get certain amounts of solar, wind at site 1, wind at site 2, and wind at site 3. That would be optimal. And what you can see is that if you use different years, let's say if we used year 3, we would, well, maybe this is the easiest. Year 4 looks pretty close, but some other years are pretty far. We build year 2 data, we build a lot more solar, and we build a lot more wind if we use year 3 data. If we use 5 years of data, we still get some distortions. What we have here is the cost. So the expected cost, the best you can do, if this repeats itself forever, is a present worth of $178 billion. And the consequences of having the wrong mix go up can be on the order of, well, this is the worst case, several percent. What is average? Average is if you use the average output in an hour across the 10 years and assume that that's what it contributes. That's truly, truly distorting. So the regret from using the wrong capacity credits, from using too small a sample, if on average, if you use just 1 year of data across all these 1 year scenarios, you've got a couple billion of regret. About half that if you use 5 years of data. So 5 years is not enough. There's still some distortion and some regret. Okay, so conclusions. What's the next thing that I want to do? We're going to throw in storage. We're going to throw in demand response. We're going to throw in constraints like certain turbines cannot be started twice a day to meet the morning and evening peak. What are their capacity contributions versus a battery versus a combustion turbine versus wind? And we're going to be throwing in unit commitment constraints, a convexified. So the theoretical result was you can get supporting prices, you can get the optimal solution, and so Jacob, of course, you're going to show how we're all wrong because we ignore risk aversion, but at least for a couple days you might think that I've done something that's valuable till he speaks. The wrong credits can distort the mix and the cost. We're talking about 0.5% or 1% inefficiency, which on an annual cost of $30 billion a year, that's pretty significant. The hypotheses are confirmed. If you undercount or overcount, the response of the resource that's under or overcounted is ambiguous. It turns out in this case there's more distortion if you overcredited rather than undercredited, which I thought was interesting, but that's not necessarily the case. It's not clear which sort of errors are going to generally be bad. And if you don't differentiate, you're going to increase costs. And of course, the theoretical result is if you need to give each resource its marginal contribution, that's probably the biggest lesson here, giving the average contribution is the biggest distortion. And with that, I'll conclude. Thank you.
Thanks very much. Do I get a microphone?
If you would like, yes.
Okay.
One quick question.
Yeah. So if I'm
That was the question. Next.
So if I'm the nemesis, then going back to the origin of the word in classical antiquity, that would make them the hubris. So thank you very much for the presentation, Ben. And it's good to see. It's good to see some theoretical analytical results on how to credit different technologies. Because certainly when we've been doing lit review, there seems to be very little analytical work in this area, or maybe we're just very bad at doing lit reviews. But I had a couple of one brief comment and then question. And the comment is that I end up having quite a lot of debates with people over whether you think about looking at capacity credits at peak of demand, raw demand or net demand, and I think one tends to get led down blind alleys doing that. And if you actually define an appropriate capacity credit metric and do a proper risk calculation, then you get the right answer. And if you try and sort of visualize it without doing the calculation, things go wrong. The question is in how this might lead to a design for a practical capacity auction, because it seems to me that the key point is whether within this you get to know the target reserve margin and the appropriate marginal capacity credits ex ante, or whether you only know them ex post once you know the economic optimum. And it looks very attractive that in this you apparently get a simple additive commodity. But does this provide a route to having a technology blind capacity auction involving with a simple additive commodity?
So that's a terrific question, and it actually gets at another issue that the West-wide resource adequacy market that was being mooted a couple of years ago stumbled across. And they said, oh, well, these betas are very nice, but how do you know them ahead of time? Because the marginal capacity contribution of any particular resource depends on the amount that's been accepted and is built in the market. It also depends on everything else going on in the market, everything else that's been added too. So if you don't know the solution ahead of time, if you can't predict the solution ahead of time, then you can't predict the right beta and RM ahead of time. So we resorted to a discussion saying, well, this is a very slow-moving system where you're having auctions every year, so you know kind of in the what neighborhood you might be in. And if we know the neighborhood of the generation mix, we can get somewhat good estimates of beta and reserve margin. But that was all, you feel the breeze from the hands being waved? That was all hand-wavy arguments with no no analysis of really how much uncertainty is there. So right now California is a year ahead market, so you pretty much know what's there, but that's also a pretty useless market because that's not going to incent, you can't get new additions within a year. PJM is a 3-year ahead market. Okay, now we can get some competition in terms of new stuff, but that adds more uncertainty to the betas. You can imagine some Wilsonian iterative market where you accept bids, calculate the betas and reserve margins, and then allow people to rebid or something. But definitely folks in practical market design don't want to go down that route at all. So you've put your finger on a definite weakness of this, that we don't understand whether we can really do this ex ante or not.
Yeah,
Darn you!
It's certainly an issue in Britain that it's certainly an issue in Britain that there's the desire, like obviously there's the desire to keep the simple additive commodity. But Stan thinks I'm about to say something stupid, so he's jumping in.
So it's an empirical question about how stable these betas and RMs might be given uncertainty, and that's the next thing I would look at. Had the discussions among the West gotten any further, but governors of Utah and others, people at higher pay grades objected to the West-wide day-ahead market, so we never got to the point of actually trying to figure that out. Do I get to choose? Do I?
Oh, thank you. Just comment on what happens in Great Britain, because we do now go to quite a lot of effort to identify the actual contribution that all these different types of resource make, and without giving them credits up front for some rules. So that's effectively something like the effective load carrying capacity,
right?
Capacity. So that automatically takes into account vocational issues, if you want to take into account vocational issues.
If you do it right.
It takes into account flexibility, in particular the flexibility that comes from storage, that you can move around and fill in gaps.
Right, and you don't need a separate flexibility product to do that. The capacity product and energy is enough.
Storage is appropriately capacity credited in the GB capacity market already on that basis. Chris makes point frequently about additivity, and a weakness of all these markets is that they try to determine in advance how much you need, which is by adding up equivalent firm capacities or whatever. But as you say, the contribution of any particular resource depends on what other resources are already in the mix. So what you should do is, in principle, you should just do some checking as you go along in your market that you are hitting the right level, just accordingly. But as you say, the fact that we have markets quite frequently, the mix isn't changing very much from year to year, does mean that you do have a fairly good idea in advance of exactly what level you're trying to hit. In GB, it's not a problem at all because you think of a particular value, and in the market you say we want 47.9 gigawatts of capacity, and then the Secretary of State makes some random variation to that and says we'll deal with that a few years down the line. So it's a theoretical problem presently.
Okay. Another way you could look at that's a first order approximation to this loss of load probability thing as a function of all the variables. Could you have a second order, something at a square terms in there? Might that be more accurate? Maybe it's not necessary if things aren't changing very quickly. First order is good enough. Bert.
Yeah, so I want to steer the discussion a bit in different directions. So one other
Enough of this.
on
Okay.
this capacity payments could be reliability options. And then basically you delegate the calculation of the betas to the wind farms because they can sell reliability options, but they might not be available, so they might have some risk. So my question is more like, who is the best place in the market to calculate those betas?
Oh.
Is this the wind farms? Is it a system operator? Or could you say, okay, this should be rating agencies or insurance companies that are going to insure those wind farms for when they're not available, and then maybe you get sort of a market setting up for the betas?
That's interesting. Okay.
So what sort of in your model is the system operator calculates the betas?
Right.
So could
that emerge from some sort of market process where people bear the consequences of something not being available, but they've accounted for that, and consumers buy portfolios of stuff or buy insurance? So I haven't even thought about that, but that's a terrific question. Anybody else like to comment on that?
I see Bert's point, but still I think the system operator needs to know how many reliability options to option, right?
Yeah, but they can just say it's okay. The question is whether you think that financial compensation for people who are not served.
I fully agree with your
Okay.
point, and I think it's really valuable. But I think still the system operator needs to have a sense of what is the capacity credit, even if it's not accredited to.
But I think then you can use a capacity factor of 1.
Yeah.
And if the wind farm does not deliver, they will have to give a financial payment.
It's just a financial incentive. It's not backed with.
Yeah, so it might not be backed, but it's sufficient to pay the consumers who are being shut down. And okay, some of the engineers might, or politicians might not like this. So you might still need some safety valves exposed to sort of check it. But okay.
I'm mindful of the time, and Sarah and I, being from the Midwest, farmers know never to stand between the cattle and the barn at feeding time. And so here I stand, and I should get out of the way, right? So we have an hour?
Yeah, for lunch.
Okay, an hour for lunch. Enjoy, and we'll see you this afternoon.